Hey guys, it's Don here. I'm bringing you today an episode, hopefully on reliability. What you can actually see in front of you at the moment is just a setup I've done with my webcam. It's actually hanging off my microphone so that it allows me to do a bit of whiteboarding. And the reason why is I kind of find it a bit easier to handwrite stuff rather than trying to type it all out on the screen, except for a few things that I'll show a little bit later just in Excel for simple calculations. A few weeks ago, I had asked on our board podcast if people were interested in an episode on reliability, and I was trying to figure out how to actually do it in a spoken only format, which I found it kind of really difficult to do. I had a go at it and I just wasn't getting very good results, so I thought perhaps a little bit better would be to actually do it as a video, and that way I could talk through concepts, I could draw stuff, I could write stuff, and so on and so forth. So hopefully it'll work a little bit better, and obviously because I'm recording this and I don't do a lot of video editing, I'm probably going to make mistakes as we go, but forgive me for that. So the first thing really about reliability is that reliability engineering is a concept that is applied through pretty much almost anything that is product designed these days. The concept of reliability obviously is that you want a product to not break down or have failures. However, one thing that a lot of people who are involved in reliability typically get frustrated about is the thought of quality is equal to reliability. And that's not always the case. A lot of people misunderstand the concepts here because quality is typically related to two things, and that's going to be materials and build. When we talk about materials, quality of materials sometimes matter, sometimes it doesn't matter, whereas build quality typically always does matter when it comes to reliability. So it's not a straightforward correlation that a higher, inverted commas, quality product is actually a more reliable product. And what I mean by that is it all comes down to function. So, if you have a hammer and you have a hammer that's built with high quality materials versus a hammer that's built with lower quality materials, there's a pretty good chance that both hammers are going to perform the same function very, very reliably for the majority of its life. And to gauge the difference between, say aircraft grade versus non-aircraft grade aluminium between two hammers, it's going to be an extremely low failure rate, and therefore the reliability between the two products is actually quite high. However, the build quality is where your differences are going to come into it, because if you have one that's built from billet aluminium and it's CNC'd out, it's going to have a different strength property compared to, say, if it was a forged hammer, because the internal molecular structure is going to be different, and therefore the stresses on it when it's being cut or when it's being forged is going to be different, and therefore so on and so forth. It'll have different physical properties, and its reliability comes down to that. So once we get away from the concept of quality equals reliability, we have a little bit more thought to play with, which is all about function. Now, how this relates to keyboard is a lot of the time people go, I want a better keyboard. I want a keyboard that's not going to break down. I want a keyboard that's more reliable, but it's often paired with this quality factor. And you'll hear us talk about this when we review or compare boards, that they'll say, it's a better build, or it uses better quality materials. So both of these factors are important. You just have to understand that it's not a straight one-to-one relationship of quality and reliability. And I'm just realizing that I'm talking a lot with my hands that you can't actually see on camera because I talk like an Italian. Sorry to stereotype, but that's just, a generalization. Okay, so let's clear the board. So the next thing then on what we talk about when we consider reliability is the functional block diagram, because in order to understand failures you have to understand functional failures. And for those who've never done anything to do with functional block diagrams, it's very simple. It's purely just a breakdown of how a system works, its major components that you're interested in for its failure or its function, and it allows you to define your boundaries. So when we talk about a keyboard, what's the actual function of a keyboard? And the output function, if we go from over here, is a signal. And this signal is basically an electronic signal or an electric signal. An electrical signal, which goes to the computer. However, what goes in is, we'll go on this side, it's a physical key press. We depress the switch, something happens, an electrical signal comes out on the other side. In between here is our keyboard black magic box. We can break it down into an actual switch, and then we can break that down into the microprocessor, because the physical key press activates the switch, which closes the circuits, which then gets converted through the microprocessor, which sends a specific electric value, which then is determined through the computer as whatever keystroke in the array. Now, at the same time, we have other relationships that can occur in here, and things like LEDs, for example. They can occur upon key press, they can occur after key press, they can be constantly on, so the branching of this is a little bit funny because it depends entirely on the actual design and setup of the keyboard. But what we do is we draw a bounding box. And for a functional block diagram, what you're interested in is knowing your inputs. So we've got a physical key press, which is an input, and we've also got power. And it's going to be USB. And then you have whatever occurs on the inside, so physical key press, and then the power. It's a little bit of a funny one because it sort of goes to the whole thing. And then your output, which is going to be your electronic signal. Now, I've actually chosen to draw this block diagram around all the components here, so I'm saying everything in this I'm going to look at. But within that, there is certain criticalities. So if the LED dies, does this actually prevent the keyboard from working? And the majority of the time is no, it doesn't, because the keyboard's going to keep on working. You just have a dead LED. Unless if it's been wired in a particular way that the LED is actually critical in the signal path or the power path. And so in that sense, that is a non-critical failure. If you have a switch and the switch fails, will the keyboard stop working? It's a yes and no. Yes, the keyboard is probably still going to keep working because the other switches will work, but it would be considered a critical failure because you want your reliability of the keyboard to be 100% switch function. And then you consider your microprocessor. So if the microprocessor fails, will you still be able to get a signal out? And the answer is no. So it's going to be a critical component of our system. So here we can already see a very basic functional block diagram where we have 3 components and 2 of them are determined to be critical components. This plays in a little bit later when we do some calculations, as well as in general the considerations of what we do. So just keep that diagram in mind. I'm sorry that I'm not able to sort of keep that on the whiteboard because I am going to clear it just in a moment at some point. Maybe I'll just leave it for the time being while I rabbit on. So when we start getting down to this, we have to think about what a functional failure is. And the functional failure is quite simple. It's all you do is you define each component and its function, and then you slap on a fails to at the front of it. So I'm just gonna slide that up a little bit. Okay, so our switch, its function is to convert a physical key press to an electronic signature. Well, not signature, signal, sorry. So an electric signal. So really it's a transducer if you want to think about it in a particular way. And so therefore the functional failure is fails to convert the physical key press to an electric signal. Okay, and then we have our microprocessor, which is to convert an electric signal to, I don't know, what would you say, to a keystroke signal. Okay, so the functional failure of the microprocessor then becomes fails to convert electrical signal to a keystroke signal. Okay. Why is this important? Why do we do this, what seems to be a very fundamental, rudimentally simplistic sentence where we just slap on fails to? And the reason is because this allows us to work out failure modes. You know, has this component actually failed? Because if you answer this question of fails to, it will tell you. So if we look at our switch, for example, fails to convert a physical key press to an electric signal. If you have a switch and you press it, you think it's broken, well, does it fail to convert a physical key press? So if you press the switch, do you get an electric signal out the back? Yes? Okay, key switch is working. No, key switch has failed. If you get a microprocessor and you put a signal into one side and it comes out the other side, has this microprocessor failed? Now, it seems a little bit strange to ask this, but sometimes we see people and they go, oh, you know, I pressed the A key and it now outputs a D. And this typically happens after, say, a liquid spill on the keyboard. The microprocessor still functions, but it now has a functional failure because it fails to convert that electrical signal to the correct keystroke signal. Okay? It's still converting signals, it's not doing it correctly to the keystroke. And that's why we define this, because now we can say, well, okay, the microprocessor is still functioning, it's not functioning correctly, and therefore it is now considered a critical failure as opposed to a non-critical failure. Okay. Now I do realize that I'm skipping maybe some important stuff along the way, and the reason why I might be doing that is not so because I'm trying to keep you in the dark, but because I do this kind of work on a day-to-day basis as part of my employment work, and some of this stuff is second nature to me, so I might not remember it as I go along. If you do have questions, of course, please ask in the comments, or you could message me on Reddit, and I'm more than happy to try and explain it, run through examples or whatnot, and even find resources online for you. Let's see if my makeshift whiteboard will clean up. it's kind of getting there. Okay. It's almost like being in high school all over again when whiteboards were being used instead of chalkboards. Little bits of scrap here and there. Okay, so now that we have functional failures and we understand a little bit more about what a critical failure is, what do we actually do with this? And what we can do is we can start doing some numbers, because at the end of the day, reliability is calculated in numbers. And there's three equations that are very simple to use that actually help us determine reliability. And the first one is mean time between failures. Good old MTBF. For a long time I would accidentally type in MBTF, I don't know why, and my boss would always pick up on my reports that I'd typed in MBTF, and she'd just be like, oh, come on, you're doing it again. So mean time between failures is simply the number of failures over the total operating time. So if you said I had, a production line and I was making keyboards and I want to know on average the mean time between failures of my keyboards, I would get, say, 10 keyboards and I would run them simultaneously, and I might discover that I will get 10 failures, but it would take 1,000,000 hours to hit 10 failures. And then so what you would end up with then, if I just crack open a calculator, because I don't do mental arithmetic, you can hear my clicky going away. The mean time, oh no, I've got my mean time between failures the other way around, and isn't it a good thing that I have a whiteboard? I'm sure an engineer somewhere was just pulling out their hair screaming, going, no, you got it wrong. It's it's time over the number of failures. I was thinking that seemed a little bit weird. So if we have 1,000,000 hours and we have 10 failures, then obviously our mean time becomes good 100,000 hours, which is, it's not a bad number of hours. Now, I'll correct that later. Put this into perspective. If you were operating something 365 days a year, 24/7, it's equivalent to roughly 8,766 hours. 90 days is 2,160 hours, I think, something like that. Okay, so, and this is 365, thereabouts. Okay, so 10 failures per million operating hours, 100,000 hours, is quite a few years before you would expect a board to fail. But this is a very simplistic calculation, and in this calculation there are a lot of things that aren't actually taken into consideration, which we'll kind of get to a little bit later. So there's mean time between failures. The next equation is what's called the failure rate. Now, failure rate is a way of standardizing your mean time between failures. Mean time between failures is really useful if you've only got a time factor, but for a lot of other probability calculations, the failure rate is what's actually used instead. They're interchangeable terms as long as you understand the relationship between them. And failure rate is also known as lambda. Excuse my dodgy lambda. Lambda is 1 over mean time between failures. So using our previous example, the failure rate is now 1 over 100,000, which gives us a very small number. 1 divided by 100 1, 2, 3, and we're looking at a 4 zeros. So yes, I don't do mental arithmetic very well. Now the units for lambda is actually per million hours. Per million hours. And this is standard. So any failure rate lambda that you see in a calculation is always scaled to this per million hours. Why? Well, I guess some equipment runs for a very long time, and it's kind of a large enough unit in terms of this small figure to do extensive systems. And when it comes down to failure rates, you can use failure rates across components, you can use failure rates across entire systems, and we do this through an additive process. So if I have lambda switch and lambda microprocessor, then the lambda of a keyboard, if it was a very simple keyboard, no LEDs, for example like a hand-wired keyboard, would equal the failure rate of the switch plus the failure rate of the microprocessor. And of course the output would still be in per million hours. This means for complex systems, every component down to the last resistor, last diode, last transistor can be calculated component by component if necessary and added together as a summation to work out a total failure rate. And I'll touch on this also a little bit later when I talk about the handbook 217 Foxtrot. So there is what failure rate and lambda is. Okay. Now how do we use these two equations, and how do we use the outputs of these equations to actually give a meaningful value? It's a very good question. We then use the reliability equation. So I'm just going to scrub that out. I realize this is getting a little bit long-winded. We've been going for 22 minutes now, and I guess it's for some people they've probably already nodded off, but if you're still here with me, thank you. So reliability, the very simple reliability equation is RT equals exponential minus lambda t, where t is time, the operational time that you want your equipment to run, lambda is our failure rate, and e is just an exponential function. Now, I actually have an Excel sheet that I've kind of tried to prepare, but obviously I gumbeat it up because I had stuff flipped around, so I'm just going to fix that right now. Equals that divided by that instead. Okay, and then let's switch on to that. Okay, so I've actually written out the three equations that I've had before. So there is your, where's my mouse? There it is, mean time between failures, which is, and that's incorrect, my apologies, more engineering hair pulling going on right there. Okay, so failures, total operating time, and then lambda, which is 1 over MTBF, and then there's the reliability equation, which is e to the minus lambda times time. So if we run through an actual example and we say we have our 10 failures, we have our operating time of 1 million hours, then there's our MTBF of 100,000 and our failure rate of 0.00001. Now if we throw our failure rate into our reliability equation and we say, well, now we have this failure rate for this keyboard that we know fails 10 times per million hours from factory testing, and we're going to give it to a consumer and we're going to say, we'll give you a 1-year warranty. Alright, so we're going to expect them to hammer this keyboard 24/7, 365, and we'll say it's 8,766 hours. And the equation now comes out and says, oh, here we go, it's a 0.916. So if we round it, it turns into 92% reliability. The consequence of this is, out of all of the keyboards that you send out there is a 92% chance that the keyboard will not fail in 8,766 hours. Let's just let that sink in. So if you had 10 keyboards fail after 1,000,000 hours of operation in your testing, on your bench testing, your lab testing, 92% of the keyboards that you send out with that exact same build of quality and materials, 92% will not fail in a year of constant use, 365, 24/7. Okay? And that's what the reliability equation tells you. Now, at this point, let's talk about the very common phrase that people use, which is planned obsolescence. And you hear it all the time. People go, oh, it's designed to fail after a year, and so that's why they only give you warranty for a year, and then your thing breaks down like the day after your warranty expires. It's actually the other way round, in that they don't design it to fail, they design it to be functional up to that point, because the probability of failure past that point increases. So just by using this very simple example, you can see that it's got a 92% probability of not failing if you were using this keyboard 24/7. But because most people don't sit there cranking away 300 actions per minute playing StarCraft 24/7, it's highly unlikely that you're actually going to be hitting a total amount of 8,766 hours in 8,766 hours. So the reality of that means your keyboard is actually more than 92% reliable. So if we take our same example here and we tweak our hours, so let's say you're on your keyboard, we'll say 16 hours a day, because you got to get a bit of sleep, you got to go to the bathroom, you got to eat, and so on and so forth. And I realize some people eat at their keyboards, but I don't know if necessarily people sleep and key press. I don't know, maybe that's one of those things that happens these days, or have a shower or a bath with their keyboard. So we'll say, just waiting for a bit of traffic to go by on the street, 16 hours a day times 365 days in a year, bam, 5,840, and you'll notice that the percentage has increased by 2%. So if you were using your keyboard non-stop 16 hours a day at this keyboard failure rate, the keyboard is now 94% reliable. Why does this matter? Well, it's very hard, virtually impossible to get 100% reliable. There's always a chance that something's going to fail, and that's just how life is. Stuff fails straight out of the box. Stuff might not fail for eons. This keyboard might have one magical keyboard which will never fail. It will run till eternity. It all comes down to the distribution curve, and it falls under various probability models out there. A very common one for probability on reliability is the Weibull distribution. However, a simple binomial distribution is also used just for very fundamental calculations. And planned obsolescence it's a funny thing. It's a funny thing to consider, because you're going to get a good item, never fails. You get really bad ones, fails all the time. And it all comes down to critical components inside. So when people start talking about mechanical keyboards as being really reliable because it's got a 50 million keystroke switch in it, you sit there and think, well, if it's got 50 million keystrokes, that's a lot of keystrokes. That's a lot of time. It would take you 115 days of non-stop spamming at 300 actions per minute. Okay, so you're going to be hitting that keystroke 300 times per minute, every hour, every minute, for 115 days before you hit 50 million keystrokes. Is that going to happen? No. Not likely in most people's lifetimes. But why do keyboards fail? And it's not because the key's unreliable. It's a mechanical switch. It's very simple, very few components within it to fail, therefore a very low failure rate. But it comes down to the electronic components. Now, a little bit of a history lesson. I'm just going to turn the Excel off for the moment. There we go. So, back in the days, and this is still true today, in that military research actually funds a lot of activity that filters down to civilian life. And a very long time ago, Bell Labs started doing a bit of testing on electronic components because they were trying to understand reliability for military use, because they needed components that could go out there and be used in a whole bunch of different environments and scenarios that were critical to military use. And we're talking about for the purposes of safety, for the purposes of delivering mission capability. You don't want it to be in the middle of a firefight and then you press a button and nothing happens because a component has failed. So they started doing a whole bunch of testing on a whole bunch of different electronic components, and reliability was really, well, electronic component reliability at this point was really founded. And they came out with this publication. Now, this publication is actually superseded, but it is still considered one of the best grounding basis publications out there for reliability. And what I'm talking about is the Mill Handbook 217 Foxtrot. This guy. Okay. This is a 1991 edition Foxtrot, and I'm not entirely sure what has superseded this exactly, but you can get this free on the internet. There's no restrictions on it whatsoever, so if you're interested in it, go search it, have a look. Approved for public release distribution unlimited. Okay, so it's not like I'm selling any secrets here. This is an excellent resource if you're interested in this stuff. It's a terrible thing and probably would put you to sleep if you weren't. So if you have difficulty sleeping, go have a read. And you'll see within the actual table of contents, we get a whole list of different electronic components. And the reason why they started doing this is because electronic components have a very difficult to predict lifespan. Their reliability is, unlike mechanical components, where mechanical components typically have a wear-in phase, a operational phase, and then a wear-out phase, where you have indicators to say this is working really well, this is starting to not work very well. And when I talk about that, I'm saying things like friction will produce wear markers, so you can see material being degraded. You can measure electrically your contacts are making a good contact or not. You can see corrosion and so on and so forth. But with electronic components, you don't have that same capability. So what they did was they took all of these different components and they set them up in various different ways, in different conditions, in their lab, and started counting how long it took for it to fail and how many times it failed under these conditions. And this is a 205-page document. It's got a whole bunch of different references to mill standards, and it explains the process and has some really funky tables. And we have this environmental symbol description table which tells you what kind of conditions your equipment is actually going to be run in, because these factors will give you different failure rate constants. So ground benign is basically sitting around in the lab. Ground fixed means it's out in a building somewhere. Ground mobile means it's like in a vehicle in the back of an APC or a moving lab, kind of like the one that you see in Die Hard 4. Naval sheltered means it's like in a sealed compartment kind of thing, like in an ops room. Naval unsheltered means it might be out on a deck somewhere or somewhere that's exposed to the elements or heat and smoke. You got airborne, in different planes, cargo planes. Rotary winged is really important because choppers have a lot of vibration involved. And then you've even got space related failure rates as well. Missiles, cannons, and so forth. And you'll see that we start getting to some heavy duty equations. Now I'm just going to randomly skip to maybe, a transistor. Okay, here we go. So here's a transistor. It's a low frequency transistor and it's a bipolar type. And the failure rate, lambda, as you can see, for P is equal to P beta, pi T, pi A, pi R, pi S, pi Q, pi E, failures per million hours. Okay? And then these tables tell you what you put inside it. So for both PNP and NPN types, lambda B is exactly the same. It's just a flat rate. There's an application factor. Is it a linear amplification or are we switching between two different circuits? And you would use whichever function you're after. Here's the temperature factor. Okay. How hot is the environment that you're in? Now, if you are operating this keyboard, or let's take this as a keyboard example. If you were using a keyboard and you were in a nice air-conditioned room at 25 degrees Celsius, it would have a factor of this row, 1.0, 105, 4.5. But now, suddenly if you find yourself in the middle of a engine room, and this keyboard is plugged into the control unit for, a diesel engine, and it's like 55 degrees, then we go to this row and it's 1.9, 135, 68. And you use these to actually work out through this small equation here what the junction temperature is, which then is fed back into, the equations and so forth. They went and did this for all of these different brackets to work out these equations. You have a power rating, so the number of watts that's actually going through the transistor will affect the pi R as well. And then you've got little mini equations here as well that can be used for calculating stuff below or above the certain ratings that they have. And even more variables, voltage stress, environmental factor, and the quality. So these abbreviations indicate the type of build materials that we're talking about. So a lower than these ones listed would have this factor, and if it was a plastic housed transistor, then it would have this factor. Once you throw it all in, it gives you a particular lambda, and that would be a good starting point. And then you can use that lambda and throw it into our reliability equation that we showed before, the RT, and the time factor involved on how long you plan to operate this piece of equipment. And now we talk about our components, in that I said you can add components together, you can sum them together to get a total system failure rate, right? If you remember, I said that a little bit earlier. If you were building something that was very critical and you knew exactly how many transistors were in here, you knew exactly how many diodes, how many resistors, how many LEDs, how many capacitors, you would use a resource like this and work out the failure rate for every single one of these components. And then you would add them together and it would give you your complete equipment failure rate. Now that sounds really painstaking. It sounds like it would take a lot of time, and it sure does if you were doing it by hand. Thanks to modern software, it's a little bit easier. For example, Windchill is a program that's used for reliability calculations. You throw in a list of the components that you have and their quality and their build factors and all that kind of stuff, and it will work it out for you because it has things like 21F, 217 Foxtrot built into it, and it can calculate all of that for you much faster than if you try to do it by hand. So there's the example of what reliability for electronic components is like. The reason why we need to use this is because electronics are hidden failures. You don't know when it fails. You can't see when it's going to fail unless if you're watching it constantly, and even components that fail don't have visible failures. Things like capacitors do, because you can see them swelling and exploding and stuff like that. You might see a resistor burn out. There might be some burn traces on the solder joints, but a lot of the time electronic components just stop working. And so that's why we need these kind of resources. And bringing it back to keyboards, that's actually the reason why keyboards fail. And it's not because the switches fail, it's because the electronics on the keyboard fail. And with distributions, going back to my whiteboard, my pen's drying out, there's a normal distribution. There's your mean, there's your two standard deviations, and so in between here will be 95%. The quality of a keyboard and the warranties that they provide you with will be related to the confidence interval, okay, the CI, that the manufacturer wants to determine for you. If it's a low quality, cheap keyboard, it might not even be a 95% confidence. They might go, well, we're satisfied 80% of the time this keyboard is going to work within a year. We can use lower quality components, lower build, and therefore we'll still hit that 80%, and we'll have X number of spare in storage to cover warranty claims. But then you might have a really high quality keyboard, say a mil-spec keyboard, and it might have a higher interval of function, and then it now becomes a 99% CI. And of course you would spend the money and get better components, better build, to ensure that. And then of course its warranty might be a 2-year warranty, or it might be a 5-year warranty, and so on and so forth. That is why you will see people have all these conflicting thoughts about the quality of a particular item, because people have good experiences, bad experiences. They'll be like, oh, don't get that keyboard, it's shit because I had it fail straight out of the box. And then somebody else might go, well, no, I've had one for like 3 years and it's been pretty reliable. People get conflicting ideas, and it's because one guy, his keyboard fell down here, and the other guy's keyboard is somewhere up here because it hasn't failed yet, and this is time. And they've got the same build, they've got the same quality, and it's because it's the electronic components in there. And you'll see a lot of people griping about LEDs burning out, and LEDs follow exactly the same process. And you can go into 217 Foxtrot and you can pull out the sheet on LEDs and you can do the calculation, and it's going to give you an X number depending on the circumstance and the quality of the LED components inside. So that's the kind of things that we talk about when it comes down to reliability. And ultimately, the most reliable keyboard is actually a hand-wired keyboard. It's the most simplest design because you don't have to worry about complex processes on a PCB with traces that could physically fail. Plus, if you don't want LEDs, you've just removed another component from your system that adds to the failure rate, because all you're left with is switches, diodes, and a microprocessor. The microprocessor fails, you can just desolder it, solder a new one on, and it's as simple as that. But of course it's a lot of effort, because then you have to program, and you have to solder, and you have to get a custom case sometimes, etc., etc. But yeah, now there is additional resources out there on reliability if you are interested. I actually tried to put it onto OBS as well, which is what I'm using to record this video with, and for some reason the overlay and page wasn't working, so I wasn't able to have it prepped as a quick turn on turn off thing. But if you're interested in seeing a couple of more tools with some very simple descriptions on reliability, what you can do is you can Google reliability toolkit, Okay. If you do that, you will see a really good website that has a whole bunch of different tools, and it's got simple descriptions on the mathematics as well as its use case. And you can throw some numbers in just for a bit of fun and play around, and it's got examples in it, I think, in some sections. And it is kind of like a gateway website. And the wiki article, while it does explain simple things about reliability, it also starts to get into some mathematical equations, which I know can be overwhelming. For me, when I first looked at it, when I started working in this field, it was a little bit much, but over time, I was able to wrap my head around it with real-world examples. And obviously, it's just part of my work that I do now. I do most of it in Excel, and I've got templated equations that I've put in, so I don't have to worry about a lot of this stuff most of the time anymore. So I don't know if that was a bit too heavy for people or not, if it was too light for people, or if people are face planted in their keyboards, but thank you for hanging with me all the way to the end if you're still here. I hope you had a bit of learning here, and just understanding what we talk about when you have reliability. And just to finish off with a real world example on reliability and obsolescence, and throwing in a bit of conspiracy theory here. In the US, in the basement of a particular building, I can't remember the exact details, there is a light bulb. It's an incandescent light bulb, and it has been on for decades. It has been burning non-stop, emitting light for extremely long. I believe it's only ever been turned off twice or something like that in its life, and they actually have, I think, a generator hooked up to it to provide emergency power in case the building power is lost, because it's the world's longest running light bulb. It was built a very long time ago. People claim, as part of a conspiracy theory, that that is the perfect example of planned obsolescence, where people are being suckered by manufacturers because manufacturers can build stuff that lasts forever, but we are getting products that are deliberately designed not to last forever so that they can make more money off us. This is an excellent example of a component, an electronic component technically, because it uses electricity, that is on the extreme high edge of that probability curve, because every other light bulb that was made in its era with the same components, with the same build quality, with the same quality of materials, has burned out, except for it. I don't know when it's going to burn out. Nobody knows. But there it is. And you can hear my lovely daughter awake in the background. Alright, well, I am going to leave it there. If you've enjoyed it, please like. I don't know if you want to share it, because if you share it, people will be like, what are you doing sharing this video? If you'd like to see more random things like this, please subscribe. If you have anything else that might be engineering or science related that is keyboard related, please leave a comment or ask on Reddit. And if it's something that I know enough about and feel confident that I can do a little session like this, then by all means we will. And yeah, hopefully we'll see you again soon in the new year, in a couple of days, with some more content as we go. So thank you for joining in, and don't forget to check out our episodes, the podcast, on the board. You can find us on theboardpodcast.com, or just keep your eye out on RMK, or you can actually find our subreddit, the board, as well on Reddit. So, as usual, until next time, happy clacking.